Well, I'm very glad we had this tea because it was getting a bit chilly out there before, Angele.
Sorry.
What was that all about?
Well, I think we explained it out there rather, didn't we?
Yeah, but I don't get it.
I think the problem really is that you're mixing up, what the bell and the person are really all of. I mean, you're a philosopher, right? You can probably help us here, This whole bell ringing thing, what's going on?
Oh, well, it's the classic problem of induction. When you observe a phenomena, can you assume that you can generalize from your observation to all such instances?
Well, yes, I think you can.
Can you?
Oh, definitely.
But what if you can't?
That's my opinion too.
Yes.
And what do you think?
I want to know what you think, because I don't know if I should think yet.
Well, that's fair. I understand that. It's a good instinct for a philosopher. Look, I think that when you are talking about induction, there's a few problems. So one is observation, which is how can we know that what we're observing is right?
Because we can trust our eyes.
We can trust our eyes, but let's say we put a camera there to check what was going on, to see if there was someone ringing the bell. Can we trust that what the camera shows is accurate?
Oh, yes.
Well, we might say so, but then we have to interpret what we're seeing.
It sounds very, very difficult. Are you on the same page as her?
Yeah, I am. In fact, you could run a couple of experiments to figure out, what the observation means. Can I try one now? Can I try an experiment?
Oh,
Sure.
Okay.
like real science right now.
I'll try an experiment. I want to see what the results are, what the observations are. Okay. Did you hear that?
Yes.
Yeah.
Did you see it?
Yes.
Yes. Well, it
What
depends
did
if
you
you're talking
see?
about the sound. I mean, you can't see the sound.
You can't see the sound. All right. So what did you hear?
Knock, knock, knock.
Knocking on the table.
Knocking on the table. So you heard knocking on the table. Now that is good observation, but it's not very accurate, right? We could have a more accurate observation, right? You didn't see it, but you heard it. So that's only one observation that you've made, not two. You can't smell the knock. We observe the world through our senses, and you only heard one of them. And what you heard was not a very accurate interpretation of what happened. We could be more accurate, like I could say, how many knocks were there?
Three.
So there's three knocks. That's a little bit
I
more
get
accurate.
that right. I'm always very good at these party games. I love party games.
Can we make predictions? So when we were at the door, there was this question of, well, whenever the bell is rung, does that mean that there will or won't be someone there? This is another philosophical issue. Can you assume that what's happened historically is representative of what might happen in the future?
Yes.
Imagine if every dog I meet is brown. Can I assume that every dog in the world is brown?
But you're not going to meet every single dog is brown because they're not all brown. Some dogs are white.
That's right. But what if I only see Banjo?
Then you have a very narrow view of the world.
Correct.
You should get out more and see more dogs.
Well, I'll take that. But when we think about science and designing an experiment, there's a question of whether we can extend and make assumptions about what we've observed, say when Tom was knocking on the table, and whether if I knocked on the table, would it sound the same as when Tom knocked on the table?
See, they weren't really observing when the doorbell rang, so the whole there's nobody there, you weren't even, able to be there to say that it was there or not there.
Well, we've only just had the doorbell put in.
So maybe there's a fault in the electronics that is making the doorbell ring. But I'll make another extension of the experiment as well, right? So just say you hear a knock. What does that make you think? You hear the knock, then you think, what was it that you thought? You heard the doorbell ring. What did you think? That there's someone at the door.
There's somebody at the door.
But
There's somebody at the door.
But that's not it.
That's not what you
valid.
said before.
That was the doorbell
You
ringing.
said,
This is the
that
knocking.
is at the door.
That-
But
and
somebody's
that's-
too.
But that's not a valid explanation of the observation that you made, right? So if I was to say, what does that mean? All that means is that there's a knock at the door. You can't say because there's a knock at the door, the conclusion to that observation is that there's someone at the door. Because that's not answering the question.
I think
I
you two
used
should
to
listen
like
to
you.
Is this a little bit like if there's nobody there to hear the tree fall in the forest, then did it really fall?
Or the sound of one hand flapping.
Is this like quantum mechanics?
Do you want me to bring in some quantum mechanics now? 'Cause
Yeah, come on.
All right, let's talk about quantum
Before you
mechanics.
start, I just want to inform the two of you that I have brought these two here to visit. And they are scientists. Yes? So you should listen to them and don't keep questioning them, okay? Because that's not how science works. Up you go.
So there's this very, very famous experiment. I'm sure you've heard it before, called the Schrödinger's cat experiment. Where
Don't
you
listen,
have,
dog.
where you have a cat in a box that through some process of exactly 50% chance, the cat will either be killed or not. Right, so after some time, it doesn't matter, the experiment says, let's say 1 hour, you know for sure that the cat is dead or alive inside a box, right? But you don't know which one. One interpretation of quantum mechanics is to say that the cat is dead or alive. Another interpretation of quantum mechanics is to say that the cat is dead and alive and everything else in between until you measure it. So if we apply that to the doorbell, when the knocking or the ringing of the doorbell, you have to assume that there is someone there and someone not there and everything else in between until you observe it.
So I have to think all about those things at the same time.
It depends on which interpretation of quantum mechanics you subscribe to. Yeah.
Got it?
Wow.
Got it, both of you?
So how do you possibly do any research when there's so many questions like this that are just messing with your head?
Cover it.
Well, I guess you just have to consider all of these things. Science isn't perfect. We make the best of what we can. We try to include as many examples of where something has been biased or not biased. We try to control for as many variables as possible, but ultimately there are some logical leaps we make, and induction is one of those leaps that we've always made with science, and we always will have to make, and we have to acknowledge that the way that we are structured, like a dog, the way that we're structured as... Oh, I'm going to wait until this dog goes past. I mean, I don't know whether dogs should be invited to tea, but, you know. We've got to consider that the way that society is structured informs the conclusions we reach. So if we have a scientific research body like we have in history, which is predominantly men, predominantly white men, with a particular view on the world, they might interpret things in a different way than if that group was more diverse. And that means that potentially sometimes conclusions in science are not right, because the process of induction is very much based on what software we're running as individuals doing that research. It's a logical leap we have to make. So you're
saying that there's not actually a scientific fact, it's just an interpretation?
Well, this is a tricky one. Some people in my field would say that everything's socially constructed. There is no such thing as a fact. A fact is something that we socially construct to be true. At the same time, we can acknowledge that we're sitting on a couch and there is a couch here, whether or not we believe that there is a couch here. But
well, we call it a couch, but...
Well, it could be something different. So a good experiment, a thought experiment, as opposed to a physical experiment like Tom would do, would be to imagine that we're all aliens. Imagine we have no idea what doorbells are, what doors are, and all we can observe is this. There's a sound.
I'm being an alien.
Yeah.
It's a very good game.
That's, yes. And then what do we interpret? That's really all we can know. But of course we don't do that.
But if we were just
we're
like
people.
an alien single-celled like algae thing, then we might not be doing very much interpretation at all. It might
Quite right.
Like there's a
just have
small
to,
vibration in the air, and that's what the sound of the bell is, and
that's it.
you
So
know,
we just
now
have to
let's
do the
move
best
on to
we can.
finding another algae cell to eat or something.
But this is why we have to acknowledge that there's always the chance that what science tells us is really what people have told us based on the process they've gone through, and it might be wrong.
But if you do physics, are they facts?
Not necessarily. They're facts as much as we can prove them with evidence, and there has been many occasions where scientific facts have been proven wrong. Newton was right until he wasn't right. There have been many times where...
What? Newton was wrong?
Newton is very right, but
Newton's
then there are some certain
laws
circumstances...
are still real, aren't they?
Yeah, of course, but in some certain circumstances they don't apply.
I think I can.
Oh, sorry.
Oh, you go first.
Well, no, I was wondering, in the application of this knowledge, do we, choose Newton when he's right for this, and then we choose somebody else when he's wrong, but it's the same foundational sort of stuff?
It's actually a really interesting part of where physics is going at the moment. I'll speak for physics because I know, right? But there's the boundary between classical and quantum mechanics. So we don't know where quantum mechanics starts and where classical mechanics ends. So yeah, if you want to figure out, where the ball's going to be when you throw it, you use Newtonian mechanics. But if you want to know where the electron is when you throw it, you use quantum mechanics.
And do they sort of argue with each other?
Yes, they do. Yeah,
But then, how can we use both?
we can't. We're trying to find the barrier between them.
Oh, I think I got a good analogy. I've been trying to get into a certain part of Australia, Western Australia, and I think I should go in, and they think I should stay out.
Yeah.
So this is a very much a dichotomy of whether I should go in or they should keep me out. So what I have brought in, which I think is exactly that point, is the Supreme Court. So they're the ones who decide whether or not I go in, yes? And I think that's a good example of where you choose whether to believe that Newton is right or wrong.
Is
That's
there
that
like a
good
Is
supreme
there a
quantum
supreme-
court?
That was my next question.
It's a great question. They call them laws, but who's the police of Newton's laws? It's a great question. I don't know. There isn't.
Wow.
Well, it's called I always get that wrong. It's called the Academy. When you publish results, your peers will review and contribute to those results, and that's how.
And that's when you pay
that's
them
one
to
of
do
the
it.
ways.
Yes.
In
Not
theory.
In
But
theory,
there's
correct.
the replication crisis.
Correct.
And there are all sorts of other things going on. And a lot of the time, I think we do look to an appeal to authority. As much as science is meant to be, anyone can peer review and anyone can do an experiment, we do look to people like Newton for these things.
And there's a huge lack of publication of null results. For example, you would not publish the fact that you went to the door and there was no one there.
Why
You would
not?
only publish when there was someone.
Because
That matches your hypothesis.
it's not very interesting either. It's not very interesting to keep saying, well, this table doesn't exist, is it? I mean, they say, well, why
I
do you
think
bother saying that?
how does the cup stay up?
Yeah, exactly.
If
That's
it's
that,
not-
yeah.
But can I say that, what happened just before shows that you're part of the establishment and I'm more of a radical in some kind of progressive new paradigm.
You're free radicals.
Free radical.
Oh, yes.
I think I want to set you free to go and radicalise somewhere else.
But that idea of a new paradigm, where there are more women and there are more, people of unspecified gender and more people of different races, changing the paradigm. So those authorities that you're talking about, they must change.
I think so. Yeah.
So who do we listen to?
As many people as you can.
But particularly me. Because
Yes.
I'm very powerful. And I have a lot of money.
Well, this is a good question. I mean, let's think about flat Earth for a moment.
About what?
Flat Earth.
Oh, flat Earth! I thought you said flatter. I was looking forward to that, but flat Earth.
You have a beautiful tie.
Oh, thank you very much. I have several.
But if we think about flat Earth,
Yes.
a lot of people who subscribe to flat Earth theories do experiments themselves in their backyards. And they seem to look scientific. They seem to be scientific. And yet, we say the Earth is not flat. The Earth is vaguely spherical. Maybe not.
Oblate spheroid.
Yeah, but observation is key. And do we trust the satellites that are in orbit telling us that the Earth is an oblate
An
sphere?
oblate spheroid, yeah.
An oblate spheroid?
Mhm.
Or do we trust the astronauts who went up into space and say that they've seen it with their own eyes?
Or do we have to go up into space ourselves
Do we?
to prove it to ourselves?
I mean, ideally not. I can't afford it.
I can.
But you might hallucinate
Let's
from lack of
talk.
oxygen.
Yeah.
You
It's
might.
all
maybe,
very
maybe
different.
that's what happened with the astronauts.
But you can't go forward if you deconstruct everything until everything just becomes one mess of Lego pieces on the table, and you can't even see where to begin with your whole life.
Right, so we just have to accept that there's always going to be an element of uncertainty, that there are elements of quantum mechanics that can't be observed at present and are theoretical. And so then we have to think about, well, how are we constructing these borders between things? How do we decide what is physics and what is chemistry and what is biology? And why is it that we put these barriers between all of these things when maybe the answer is some mix of all of them? Like quantum mechanics, it's a bit of a mix of philosophy and a bit of a mix of physics and
Yeah.
and all sorts. Maybe that's a good way of going about it, as well as diversifying the people doing it, cutting down some of the boundaries and the siloing effect within the institution itself and the way it works. What do you think, Tom?
I think, yes, we should listen to as many people as we can, kind of marry up all of these different areas, because you're probably going to get some nice results. I mean, half the groups that I deal with are, astroparticle physicists. So these are people looking at the tiniest elements in the universe to explain the biggest thing in the universe, right? So these people are working together. It's really fascinating.
Wow.
Can you tell us a bit more, both of you, about your work? I'm really fascinated, especially since Clive told us it was, Nobel Prize material. What are you doing in more detail?
Tom, would you like to talk about your Nobel Prize?
I do not have a Nobel Prize.
Oh, that was just metaphorical.
Oh.
A Nobel Prize is a very prestigious prize given to people who change the world through experiments, and I've not done that.
You will, I'm sure.
Yeah, sure.
Yeah.
The work I do is about education. So, I did an experiment before, and the reason I did that experiment is because the research that I do tries to show how experiments help with understanding a concept. And it's not as if you don't understand the concept of, hearing a sound and making an observation, but from my research, it helps when you do an experiment hands-on, that sort of stuff.
Even if you know what the result is going to be.
Yeah, exactly. Because
But I
part
think
of
we
science
dug
is doing
deeper
the skill.
into it. We
Yeah.
got deeper insights.
To do the skill, or to understand the process of how we do science, we can learn about it in books. We can read about it. We can watch it on YouTube. But doing it is very different. To understand the concepts, but also the skills, and that's what I'm trying to do. I'm trying to figure out what it is about an experiment that helps a student learn a concept.
Can you give us an example?
An example is we've got
What about exploding things? That was always my favourite bit in science classes. Exploding stuff is good fun. Setting fire to things. I once got kicked out of the science lab. I got excluded from class when I was in year 9, I think, because we were throwing flour on the Bunsen burner to observe how combustion happens and the oxygenation. And I developed a bit of a flick of the wrist that led to a slight scorching of the roof of the science lab, and I was kicked out of class. It's the only time I ever got kicked out of class, but a good reason to do it.
I have an example that I use with students, which is it's kind of delving into a bit of quantum mechanics for Year 12 students. And it's a tough thing to understand, quantum mechanics, because it's not a realm that we're used to. We're used to classical mechanics, not quantum mechanics. So to show students how this works and get them to do the measurements and then use the data that they've got to draw a graph and interpret that graph. This is an example. It's the experiment that Einstein got the Nobel Prize for, which is called the photoelectric effect. You get a student to do it, tinker around with the stuff, then draw a graph, analyze the data, and it really clicks with them because they've done that process. Demonstrably, measurably so, which is cool.
So when Einstein first did the experiment, was he trying to prove something that he already believed to be true, or was it just chance?
It wasn't chance. He was working on a problem that was existing in physics at the time. It was kind of the birth of quantum mechanics, because they were trying to figure out, there was a theory that said the sun should do this thing, and then they observed the sun and it didn't do that thing. So they're trying to figure out what the problem was.
Just did its own thing.
It did its own thing.
Oh, wow.
And of course, Einstein's wife contributed.
Yes, Einstein's wife did contribute. Yeah.
But he
She
didn't-
made him the cup of tea, yeah?
Well,
more than that, I think.
There's some suggestion that
As well
she
as
actually
the
did a
maths.
lot of the research that he published. She
Really?
was a very talented mathematician.
But that's cheating. That's not fair.
Well, and this is what is important about doing history of science, is that sometimes we change our mindset, and it's like Tom was saying with, when you do an experiment yourself and you go through, you understand it more. So when we investigate what's in our science textbooks and do a little bit of history and look at things from a fresh perspective, we find new things.
Yeah, that was around the time where women weren't allowed to go to university because they were married or pregnant or something.
Are you married?
Me? Yeah.
And you're still at university.
God, yes.
That's wonderful. So tell me, what are you doing? What's your focus?
Well, I study scientists,
Mm-hmm.
and I basically have groups of scientists, and I infiltrate those groups of scientists. I become one of them, and then I ask them
You wouldn't stick out at
questions.
all.
No, I mean nothing about this really
I love your
would stick
shoes.
out. Thank you. So I go to groups of scientists and I ask them questions about what they do and how they do it and why they do it. And I ask them to explain to me every step of their research, because my research is taking a look at science and how we do it in Australia in particular, and then seeing what I can draw from that about, I suppose, how we socially construct ideas.
So, like, what do you see when you study that scientist there?
Well, I don't know. I'd have to ask Tom some questions.
Oh, so you can't, like, do it quickly.
Oh, sure.
It takes years.
You can do an example now.
Absolutely.
Go with it.
So, Tom, tell me about how you think about the ethics of teaching and communicating science.
I think a lot about the ethics because to get good results from the students that I'm asking questions of, I asked through surveys. To get good results, you have to make sure that the students are not feeling in any way coerced, because that's going to give you a different result. So I think very strongly about the ethics because I know that if you don't, you won't get the results that you're after.
So, see, if I was to analyse Tom's response, what I see from that is that Tom does have a sense of ethical, what is right and wrong, but that ethics is very much tied to the results, which is, if it's ethically wrong, the results will not be as good. And Tom's approach is to lean on process in order to reduce the likelihood both of an ethical breach of his personal code, but also of the chance that the science may not end up being as good. So by emphasizing the scientific method and the process of doing research and the ethics process, Tom is approaching his science in that way. So that tells me, if I'm studying Tom's research group, that I need to go and look at what their processes are, what their procedures are, and then I might come back and watch what Tom does and see if he does follow those procedures and processes. And where there's a divergence, I might ask, what's going on here? And over time, I can form a picture of how we actually do science.
He might have been coerced to say that.
He could have been. He could have been. And I mean, you know, it's high pressure. Here we are. We're having tea in our beautiful house. We don't want to get kicked out again. It was chilly out there.
So you're a bit like an auditor.
I suppose so. I would prefer to think of myself as a sort of investigative spy. I often think of that because I'm looking for the spaces between things. I'm looking for the bits that don't make sense. And I'm putting all of the pieces together to form a picture, to look at something in a new way. So I guess I'm an academic spy, yeah.
And how do you present the results of what you discover?
Well, I write papers. I am currently writing a book. And I try to use stories and analogies in how I write. And I basically would, if I was writing about Tom, would try to write about Tom in a way that is sympathetic. So it's not about saying, oh, Tom did a bad thing because he broke protocol one time, for example. It's about saying, this is what Tom does, and this is what the framework is, and this is why Tom does the things that Tom does. And the person reading this will then understand a bit more about it, you know, rather than starting from a top down of, like an auditor would, of here's the process. Now is Tom following the process? I prefer to start with Tom.
So he's like trying, you know, you've got Tom compassion.
Always.
For him, his attempts to be a good scientist that sometimes, you know.
I mean, there's this guy called Bruno Latour, who is a sociologist of science and wrote these amazing works where he would do things like pretend he was an alien and look at what was going on in a science lab. And Bruno Latour said that you have to love your technologies, because if you don't love them, then they don't get supported, and it's all about the way as a society we value things. And I have to, as an academic spy, fall in love with my research subjects and in love with their projects and see things through their eyes. So I think in that way I'm able to write in a way that is compelling.
So are you in love with all of science, or are you just doing little pieces? What's your specific favourite love top of science?
Well, most of what I do is to do with space. So mostly I study scientists who are doing space sciences in Australia. And the ones I'm studying at the moment are trying to fire a giant laser at pieces of space debris to move them in orbit.
Whoa, cool.
Very cool.
In the orbit.
Yeah, so you've got Earth. What was it? An
Oblate spheroid.
An oblate spheroid. You've got orbits. You've got space debris or space junk whizzing around very fast in high numbers. And the idea is that if we go from Australia and we fire a giant laser, currently they've got a 10 kilowatt laser, at the piece of debris in orbit, and we use adaptive optics to adjust the wave fronts so that it's as powerful as possible. The photon pressure can nudge it just a little bit each time it goes round and bring it closer in towards our atmosphere and cause it to burn up, or just move it out of the way of something important like the ISS. So it's a very cool experiment, and I love that. I love the technology, but I love the people most of all. I love the way that they think about things and the way that they are so passionate about what they do.
But there's no ethical dilemma there. They're saving humanity and satellites and, technology and stuff.
Or are they?
But,
This is the dual use problem. If I have a 10 kilowatt laser that I can fire at a piece of space junk, what's stopping me from firing that 10 kilowatt laser at the ISS? Could be a weapon.
Whoa.
The ISS, that's the International...
Space Station. I knew that.
I think you had plans to buy it at one point.
Yeah.
Was that one of my many projects?
Surely you own it, Clive.
Yeah.
Turning it into a hotel.
Okay.
Yeah, that sounds about right.
Yeah.
Elon Musk and I work together quite often.
So this laser... So we've got one here in Australia.
We do.
How many are there around the world?
Well, it's hard to know.
Okay.
What
I'm
if I
afraid
bought...
I could tell you, but I would have to
But
kill you.
are they all in safe hands?
Again, that's classified.
I've had
I
a
don't know.
great idea though. What
Yes.
if I buy like 1 million lasers?
Yeah.
I could do that because I'm very rich. And then I could spread them out where they would do the most use. I could do that tomorrow. Would that be a good plan?
I don't know.
Depending on how you're going to use them.
What do you think?
No.
Have you got ethics approval for this?
Well, I mean, I have my own ethics, so I prove everything I do basically.
10 kilowatt hours doesn't sound very much.
What was that?
No, it's kilowatts, not kilowatt hours.
10 kilowatts. It's a lot.
The laser you
Yeah.
have, the little pointy laser you have on the end of a pen would be less than 1 milliwatt. So this is 1 million times more powerful than that.
If I was to turn on that laser here now, if it was sitting here and I said, Tom, press the button, it would burn a hole through the wall and through every house on this street, pretty much to the horizon, as far as you could see.
Cool.
Wow.
Yeah, it's
But
awesome.
also
Yeah.
uncool.
I
So
mean,
this-
who doesn't love lasers?
So this space junk.
Yeah.
Now I know I've read that there's a big problem with the amount of space junk up there.
Mm.
So this technology, primarily, do want to be used to get rid of the space junk to make it burn up?
Well, this is the complexity. What happens to a technology that is built in the name of science for good civil activities that might, appear in our textbooks?
Mm-hmm.
Like, what happens when you've got scientists working on splitting the atom?
Ah.
And then what happens if humans decide that they want to have a conflict? This is the deep messiness of science and technology, the complexity of the ethics, and I think it's just so interesting. I love it.
Mm.
And it's very real for people like Tom, who I would study, in that.
So
you have
is
to
there
know-
an answer to the ethics?
Is there an answer?
Yeah.
You're
What are we
asking
gonna
me to
do
tell
about
you
the
the
laser?
conclusion of my research.
Yeah.
That's unethical.
That's
No.
unethical.
You have to buy the book.
Oh,
I'm
what-
joking.
What's your book called, by the way?
Hasn't been written yet.
Oh.
That's a funny name.
Yeah.
Really
That's
philosophical.
very good. That's very good. Yeah, Schrödinger's book.
Schrodinger's book. Yeah.
Yeah.
I think my conclusion is that the way that we engage ethically with technologies is changing over time, in Australia in particular. And we used to be very divided between this is science and this is the military. And the military-industrial complex is becoming ever more complex and overlaid in Australia. And the people working on these projects know that. And I think it's something that needs to be brought out and discussed in the open.
Do we need to stop, using science for purposes of money?
What? Sorry, I came in late. What was that?
Well, if scientific pursuits are bound by, the need to make money in the same way that other pursuits are, well, doesn't that stuff up all the science?
It can do. There's a great example of that. There was a research that came out a number of years ago that said that chewing gum improves your exam results. So if you chew gum for 15 minutes before you go into an exam, you will get better results. And it was proven. Like the paper was published, and the results were there. Significant improvement in
Wow.
in results. But this was measured against people who had no food before an exam, so they just gave them chewing gum, and it was funded by Wrigley's. It can. There were results, but you have to question the results. So if you're going to do research that is funded by someone in order to get more, publicity, money, or something, that goes into ethics and also bad science. But,
Money maybe is just fundamentally unethical.
No.
So,
Yeah, it is, man.
No, it's like saying
Yeah,
a knife is fundamentally unethical because you can use it to stab somebody. This is a very old argument which I think you may not know about. The knife is just there, it's just a knife. It's just a knife, and it's not
guns
unethical.
don't kill
And nor is
people.
money.
People
That's
with
when-
guns kill people.
It's, I'm with my, I have the money, so if there's any problem with ethics, it's about me, not about my money.
Yeah.
Okay.
It definitely muddles things up though, doesn't it? Because even if the research about chewing gum was totally good, totally right, even if they'd done a really good experiment, had great data, which they did, when we look at who funded that study, you might give slightly less weight to it because it was funded by Wrigley's. But the science itself could be perfectly good. But I guess we always leave ourselves open to criticism. And it's hard for scientists, and I think it's so hard for scientists working in the real world because, of course, they do have to eat. So each of them has to make their own Faustian pact. They have to
Yeah.
deal with the devil, and they choose their devil.
Me
and
too.
they
Too.
don't.
It's very hard actually being a billionaire. It's so many decisions you have to make. It's a problem. You have so much money. What do you do with it? It keeps me awake at night
Whoa,
sometimes.
I'm really sorry for you, Clive.
Yeah.
I'm sorry to hear that.
Yeah, I'll help you with your money if you like.
Oh, but yes, I have
Yeah.
people helping me with the problems. But
We
you're
could-
welcome to come aboard.
We
Just
could use that.
give me the money
Yeah.
and I'll be fine.
Well, I do give lots of money away.
Yes.
So it's the devil or the deep blue sea.
Sure.
Yeah.
And, what's that? Blue sky research?
Blue sky research.
We should
This-
call it deep blue sea
I've
research.
never quite understood that. What is blue sky?
Blue sky research is the research you do when you think about things. You're looking up at the blue sky. It's just, well, that's the way I think about it anyway. It's just research for the sake of research. You just want to know something cool. There's no impact, immediate impact to technology or problem solving. It's just you want to know about it, and that's an important part of science because out of that comes implications in
But I
technology.
bet that doesn't get much funding.
It does not get a lot of funding because it's difficult to justify.
It used to, though.
It used to.
This is fascinating. During the Cold War, that sort of science got loads of funding because the idea was that you could fight communism by ideologically having Western scientists doing this sort of blue sky research.
Maybe that's why it's called blue sky, because it was the opposite of red sky.
Maybe.
Yeah.
But I
But
think over
that's a good
time
one.
that's...
The Russians were so good. They like invented everything. Every conference you go to, someone pops up and says, "Yeah, but this was discovered back in 1949 by Lebedov in the Smirsk Institute."
Duh.
Do you speak Russian?
My
Just-
Chinese
just
is
that.
better. But this is very true, and we've got examples of Soviet scientists working separately from other scientists and coming together, say in the 1980s or 70s, and having discussions where they say, "Oh yes, but we solved this and here's our solution." And the other one saying, "Oh yeah, but we solved it and here's our solution." And there's this exchange of knowledge because they were separate for a time, actively separated. They didn't get
So
to
it
go
was
to conferences.
good in a way that they were separated.
Well, I wouldn't go that far.
It's good that we came together.
Well, yes.
And
But had-
imagine that the more things we could do if we bring in everything, every culture around, and this brings it back to inclusivity, right? We're bringing everything
You know,
together.
that's a beautiful idea.
I come across this a lot. This is a wonderful example where you hear, "Oh, we've just discovered this sun and this thing, and it does this and this," and then the indigenous people of Australia who've been around for 80,000 years said, "Yeah, we knew that about 30,000 years ago." It happens all the time.
Yeah.
So if only we could include everybody, we might get
I think
further.
it's a great point on which to stop because we have another couple of people to visit and to get tea from because that's what we're doing today. It's really nice.
Well, that's where are you going?
Was it your friend this time?
What's that?
The person we're visiting next, is it one of your friends? Or
I
was
think we're going to build rockets,
Yeah, sure.
model
That's right,
rockets.
that's right.
I mean,
She's going to show me, and I'm going to think about putting money into that too.
This afternoon.
This
Model
afternoon,
rockets.
model rockets.
Oh,
So
how marvellous.
we'll see how high they can fly.
Okay.
can I ask,
Yeah.
like, was there someone there, though? When you heard the door,
Let's
what do
go
you
to
think?
this again.
Was there someone there? I want to know what you think. Was there someone
I
there?
think
I want more
there was
tea.
somebody there and there wasn't somebody there.
Totally.
Schrodinger's doorbell.
Schrödinger's doorbell.